I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
My name is Walter Kiefer. I'm a senior staff scientist at the Lunar and Planetary Institute in Houston. My goal today in this talk is to give you a presentation about what we know about the moon's interior. I'll start with how we know it. The Apollo experiments that are the foundation for it, the orbital data such as GRAIL that have extended the data to the whole moon. We'll talk about what we know about the structure of the moon, starting with the crust and working our way down through the mantle and the core. And I'll end with what are some of the key unanswered questions and how we could answer them by going back with a new set of experiments. An important piece of what we know about the moon, the internal structure of the moon, comes from the experiments that the Apollo missions left behind. All of the Apollo missions deployed experiments of various sorts that were left and operated for various lengths of time. On Apollo 11, they only lasted for a few weeks, but beginning on Apollo 12, they were powered by nuclear power, and the experiments actually lasted, in some cases, until late 1977. So we had a network of geophysical stations that were in place for 8 years. The most important of the experiments for the internal structure of the moon was the passive seismometer. The seismometer listened for moonquakes, essentially. It detected more than 7,000 moonquakes over the course of that 8-year period, plus more than 1,700 meteorite impacts. In this picture, the package in the front of the picture that's covered by a silver insulating blanket is the seismometer. That's there because you want to keep the seismometer at a constant temperature and protect it from the effects of solar radiation. Behind it is the central station, the control electronics essentially for the experiment network and the radio system pointing to the Earth. And behind that is the nuclear power source that powered this. So the seismometers were a key experiment, but there were other experiments that were deployed as well. The only experiment that's still operational on the moon is called the laser ranging retroreflector. This is an unpowered experiment. A laser beam is pointed through a large telescope on the Earth, and they target these reflectors and they measure the time of flight of the laser beam from the Earth to the moon and back again. So you can measure how the moon moves around the Earth, but more importantly, you can measure the deformation of the moon from tidal effects. And by measuring how the moon responds to the Earth's tides, and by doing this at several different stations, 3 stations on Apollo, but also 2 stations deployed by Russian rovers, we can actually learn a lot about the internal structure of the moon by seeing how the moon responds to tides. The third experiment that's important here is the magnetometer. The moon has no internal magnetic field at present, although it did once in the past, but the moon responds as it moves in and out of the Earth's magnetic field. And so by measuring the response of the moon to the Earth's magnetic field, we can learn things like how big is the core, which it responds to the presence of metal, but it also responds to electrical conductors in the mantle, so that's a function of the temperature of the mantle and the water content of the mantle and the size of the metal core. And so the magnetometer has been a key to understanding some of those issues. The final one is called the heat flow experiment, and on 3 missions, they drilled holes down to as deep as 2.5 meters below the surface. They deployed thermal probes that were accurate to about 1/100th of a degree Celsius. By measuring the rate at which temperature increases with depth, we can know how heat is coming out, but it was an important experiment in terms of knowing how the moon is releasing energy at present. So this map shows the 4 locations where Apollos 12, 14, 15, and 16 deployed long-lived seismometers. And because Apollo 12 and 14 were very close to each other, in effect, that's a triangular network in the central part of the moon. So it's important to our story here that the seismometers are deployed in a limited part of the moon because the longer the separation between the stations, basically the deeper you're able to see into the interior. And so while this network of seismic stations does see down to the core, If we deploy a new network in the future, scientists would like to deploy them with a larger spacing because it gives us a better sensitivity to the deep structure of the moon. And so, well, this network was a great start. You'll see at the end that we would like to have a more global distribution. So in addition to the surface experiments deployed by Apollo, a variety of orbital experiments have been flown. The most important of those was the mission that NASA called GRAIL, the Gravity Recovery and Interior Laboratory. This was a mission flown in 2012 that mapped the gravity of the moon to a very exquisite detail. These were actually two spacecraft that were in the same orbit around the moon. So these experiments gave us a very detailed map of how the moon's gravity varies from place to place, and it lets us take the data that we know from Apollo and use the Apollo context and spread it out to the moon as a whole. And in addition to GRAIL, there were a number of other orbital spacecraft that have been of importance. The Lunar Reconnaissance Orbiter has provided us topography data that we need to interpret the gravity. LRO is still in orbit today. Magnetometers from orbit from the Lunar Prospector mission in the late 1990s and from the Japanese Kaguya spacecraft in 2008 have mapped the magnetic field from orbit, and that supplements the observations that Apollo made. So all of these experiments provide a context for understanding what Apollo did. So what we know out of all of this data is that the moon is what we would call a stratified object. It's differentiated into a crust, a mantle, and a core. The crust is the outer layer. It's made of silicates, which is to say it's rocky material. The mantle is the thickest layer of the moon. It's also made of silicates, but of somewhat different composition, and you melt the mantle to make the crustal rocks. And then in the deep inside of the moon is the core, which is an iron-rich, it's a metallic area, mostly iron, but with some other things like sulfur and possibly carbon. And we'll talk about the structure of each of these layers as we go through the rest of the talk. So the image we have here shows the topography of the moon. So on the left we have the near side of the moon, and what you'll notice if you think about the dark areas that are the eyes of the man in the moon when you're looking at the full moon. These are places that are topographically low. Notice that on the far side of the moon, the topography is much higher. That's where the red shows up. But also the deepest parts of the moon is in the large impact basin called the South Pole Aitken Basin, near the bottom of the far side, near the South Pole. So this is a gravity map from the GRAIL mission. Again, the colors show the strength of the gravity field. So the red areas are the strongest gravity, and then yellow and green are smaller, and the blues are the lowest gravity of all. We would expect ordinarily that places that are low, like the impact basins, like Mare Imbrium, like Mare Serenitatis, the eyes of the man in the moon, because they're topographically low, we would expect the gravity to be low as well. And it was a great surprise when Lunar Orbiter started mapping the moon photographically in the late 1960s before Apollo. Tracking of that mission, of those missions, 5 of them, showed that actually the gravity was highest over these impact basins. They use the term mass-con for mass concentration. So there has to be some place, since it's not topography, since there's not a volume of rock, we know that the rocks that are there must be denser than the rest of the rocks and surrounding it. So the density of the plagioclase, the anorthosite rocks, the light gray rocks, is relatively low. Partly the answer to why the gravity is high in places like Mare Imbrium is that the basalt is denser, but there's not enough of it to explain the difference. And so in fact, what we know from modeling the GRAIL gravity data is that the mantle comes very close to the surface in these areas. And so we've actually been able with GRAIL data to make a map of crustal thickness. The crust is thin in places like Mare Imbrium and Mare Serenitatis, the blue areas on this map. And in some of those places like Mare Crisium, or on the far side of the moon, Mare Moscoviense, the crust may go almost to zero thickness. On the other hand, the crust is thickest on the far side of the moon, the reds and the whites on the right side of this image. So the moon varies its crust varies in thickness from about almost 0 to about 80 kilometers, but it averages somewhere between 35 and 43 kilometers in thickness. That's the overall best number from the combination of GRAIL and the Apollo seismometers. And we can use this data to get more details. And so, for example, this shows us detail of the MARE ORIENTALE impact basin. We often use ORIENTALE as an example for studying this because it's the youngest of the large basins on the moon, so it's the freshest and best preserved basin. What this shows in the upper part of this image, the green is the mantle of the moon, and it comes very close to the surface here. There's a red cap of impact melt. This is the original crust here was completely thrown away by the impact. This is the impact here made a basin that's a little over 900 kilometers across. It's almost the size of the state of Texas. And so all of the original crust was blown away. The impact melted part of the mantle. It created some additional new crust that we call impact melt. And what we know from modeling the GRAIL gravity data is that impact melt sheet is about 10 kilometers thick. And you might think, well, okay, that's a kind of esoteric thing. Do we really care how much melt was produced? And it turns out, actually, we do. The reason for that is the amount of melt that is produced is related to the size of the impact, the energy of the impact. Energy is a function of the size of the impact and the velocity, and we have a pretty good idea of the range of velocities that can hit the Earth or the Moon. And so what we can effectively do is calibrate, using the GRAIL data and using computer models, we can calibrate how big the impactors were that made these different size impacts. And that's a useful thing to do because the Moon preserves the structure of these impact basins. Oriental Basin happened around 3.8 billion years ago. It's the youngest of the basins. There are about 80 of these basins that are older than it on the Moon. But all of them are preserved on the Moon. The Earth had these impacts as well. It's just that the Earth's record from that far back in history has been destroyed by later plate tectonics and weathering and erosion, so we don't see that evidence. So we go to the Moon, we use the Moon as a witness plate to tell us about processes that happened on the early Earth and in the early solar system. It affected other planets like Venus and Mars. But the Moon is a great place to go and learn about the earliest history of the solar system because it's still preserved there. And the gravity data is a good way to learn about it. And ultimately, someday, seismometers there in this impact basin might tell us well. The lower part of this image shows on a larger scale places where we think from mapping on photos that there are faults associated with forming the impact basin, and we can actually look at structures in the gravity field. We can actually see the faults. We can see how they project into the ground in the gravity data, and that was an amazing discovery with GRAIL. And again, this is something we can do to learn about the structure of large impact basins, the process that shaped the Earth as well as other parts of the solar system. GRAIL also tells us about smaller scale structures, about things like volcanism. The particular image here is of the largest volcanic field on the Moon called the MARIUS Hills. The MARIUS Hills has about 250 small volcanic domes. Most of them are only 5 to 10 kilometers across and maybe a few hundred meters high. But they're in an area about 200 to 250 kilometers across. And the interesting question has always been, well, how did they get fed? And with GRAIL data, we can actually see that there is a high gravity structure. The large red structure in the upper part of this map is a high area of gravity. And again, just like with the mass cons that we talked about with Mare Imbrium, you cannot explain the gravity here from the topography. There must be something dense in the interior. And so we can actually model the structure, and this structure is between 200 and 250 kilometers across. It's between 3 and 6 kilometers deep. It's where the magma came up from the deep interior, much of it ponded in what geologists call dikes and sills. These are structures that form where basalt intrudes into the less dense crust, into the less dense anorthosite, and we can't distinguish between whether they're horizontal sills or vertical dikes. with the gravity data. We just know that it's a combination of those processes. But what we can see is the overall set of structures here is in effect the magma chamber that fed this volcanic field 3.8 billion years ago. So what I'd like to do now is turn to looking into the structure of the moon from the crust down to the core from the Apollo experiments. A lot of this is learned from lunar seismograms, from the measurements of earthquakes, or moonquakes, I guess I should say, as they propagated through the moon. This is an example of a seismogram. When this moonquake occurred, things started happening and seismic waves propagate through it. It takes different paths through the moon, and so they arrive at different times. And so the first arrivals are not very large, and the ones that take longer paths through the moon come in later, but they rattle the moon more. Scientists use the waves that take these different paths to learn about the velocity of the moon, how the speed at which these waves propagate at different depths in the moon, which tells us about the composition of the moon. For each moonquake, we make these measurements in actually 3 different axes. We measure the up and down motion, the east-west motion, and the north-south motion. And it's that combination of motions in 3 dimensions that helps scientists identify which phase is which on a seismogram like this. So what we know then from this is we've learned about the structure of the moon working downward. And let's talk first about the crust. So this image shows a cross-section of what the crust of the moon looks like. The crust of the moon is continually broken up by impacts. We talked before about the large impacts early in lunar history, but small impacts continue to break and jumble up the crust. So the upper roughly 10 meters of the crust is very highly broken up. It's what we call breccia or regolith. It's very highly broken up, very porous. It has a very low seismic velocity. It's very weak rocks often. They tended to fall apart when astronauts pick them up if this very near surface material. It's what forms what we would sometimes call the lunar soil. As we go deeper, the rock still has some mechanical strength, but it's still very broken up. A lot of it is ejected from large impacts, and as you go deeper yet, it's intact crust, but it's highly fractured, and the fractures become less and less as you go deeper. This rock is porous, a combination of basically open spaces in the rock and fractures. This disconnected aspect of the rock means the seismic velocities are low, so we can measure it with seismology. But because it's got these open fractures that have no rock in them, they are less dense than other rocks, and so we actually can see in the Grail data, we can actually make this out as well. And what we can tell in both cases is that as we go from the surface down to about 20 or 25 kilometers, we're going from this highly porous, highly fractured rock to this more interconnected and intact rock. And we get equivalent answers basically from the seismology and from the Grail observations. So as we then look deeper, this shows the seismic velocities from the surface of the moon with depth all the way to the core of the moon. There are 2 different kinds of seismic waves that are important. The 2 prominent kinds are what we call P waves and S waves, and they're different types of waves. They travel at different velocity. P waves are faster waves, and S waves are slower. The other interesting thing is S waves or shear waves do not propagate through liquids, so they actually tell us if the moon has liquid in its deep interior. We expect that as you go deeper, the higher pressure will cause the rocks to be denser and seismically faster. That's what happens on the Earth. On the moon, because the gravity is so small, that effect is actually not very large, and so we keep the same kind of mineral phases throughout most of the lunar mantle. The velocities that we see here are most consistent with a mantle made of mostly the minerals olivine and orthopyroxene. And if we look at the S waves, the black line, they are very nearly constant velocity all the way down. The data is not good enough to let us make a continuous curve, and so they estimate it in a few depth increments. But the differences in the velocities that you see in those different depths, they're very small offsets. They're actually smaller than the uncertainty in the data. So in effect, it's more or less a constant velocity all the way down in the white area of that graph, that is in the mantle. On the other hand, if we're looking at the P-wave velocities, the red curve in this figure, near 800 kilometers depth, there's a big jump in the velocities. It's about 3 times as large as what we think the uncertainty in the measurements are. So that would suggest that there's a change in composition there. We know that the moon was molten early on. Probably all of the terrestrial planets were. But again, just like with the impact basins, understanding the structure that's left behind in the magma ocean is something that we can learn about, use the moon to learn about what happened on the Earth. So the interesting thing here is that the change that we see near 800 kilometers in the P waves might reflect a place where there was a change in the way things were forming as the magma ocean is solidifying. We don't really understand why there's a difference in the behavior of the S and the P waves at that depth. That's something that we'll need to work out in the future. It really is scientifically important if we're going to understand the role of magma oceans early on. As we go deeper into the planet, the seismic data suggests that within about 500 kilometers of the bottom of the moon, that is to say about 1,200 kilometers from the surface, there is a layer that is maybe partially molten, somewhere between 5 and 30% of that layer of rock. And this is still a part of the mantle. It's silicate. It's made of silicon and oxygen and magnesium and some iron. But it's not metal. It's rocky material, and we think that material is partially melted, and that was a surprise because the moon is a small object. It should have cooled off, and we don't really understand. The moon should not have retained enough heat to keep it molten that deep in its interior. So our best explanation is that probably as the moon solidified from the magma ocean, that it retained radioactive material deep in the moon, and that is the source for keeping it hot to the present day. But I should emphasize that the seismic data is really near the limits of what it can do at these great depths, and this is something we'd like to get back to in the future with a new seismic network. Below that layer, the moon has a small core, about 350 kilometers in radius from the base. The seismic data suggests that the outer part of the core it's a metal. It suggests that the outer part of the core is liquid and the deeper part is solid. That's not really a surprise because the moon probably has, in addition to the iron, it probably has some sulfur or some carbon in it. Those act like antifreeze in iron, and so they would actually keep part of the core liquid to the present day. So that part of it's not really a mystery. The real mystery here in the seismic data is the partially molten layer, the yellow layer in this figure. Now I should say this is a place where the laser reflector experiments from Apollo and Grail data together have also been able to tell us things. The laser reflectors tell us about how the tides affect the surface of the moon, and that reflects the motions all the way through the interior. And if you've got a partially molten area, it's weaker, and so it deforms differently than if it was solid. So the tidal response of the moon to the Earth's tides is affected by whether it's molten or not. And Grail sees as things move up and down, that changes the gravity signature slightly. So again, Grail has a way of seeing the nature of this. And the conclusion from that is a definite maybe. The data permits that there is a deep molten layer, but it's not certain in either the laser ranging data or in the Grail gravity data. And it's really at the limits of what the seismic data can do. This is a place where we really would benefit from sending a new generation of seismometers back. So another interesting question then is, well, what type of moonquakes are there? And there really are 3 different types. A small number, 28 in all, about 4 a year, are what we call shallow moonquakes. They can be relatively large. They reach a magnitude on Earth of about what would be on the Earth of 4.2. That's big enough that if you're near it, you would feel it. The Apollo data doesn't constrain their depth very well, except that it was close to the surface, less than 200 kilometers below the surface. And the cause is not very well known. But recent observations from Lunar Reconnaissance Orbiter suggest that these are probably associated with scarps that look like faults in various places of the moon. So we can actually identify where they may be occurring that way, and that would suggest that they're very close to the surface. We do know that these events, when they happen, have a great deal of high-frequency shaking. It's a very, very pronounced rattling. These would not be good places to put a moon base because, on Earth, if an earthquake happens and your roof collapses, it's a problem. But if your roof collapses on a moon base and you lose your air, it's a tragedy. So there are some places we wouldn't want to be on the moon, and further understanding this before we build a moon base might be a good thing. A much larger set of events is what we call the deep moonquakes. There are more than 7,000 of these detected by the Apollo missions, and they were highly repetitive in about 300 clusters on the moon, of which about 100 of them occurred well enough that we could actually locate where they occurred. Mostly they're between 700 and 1,100 kilometers depth. They seem to occur in the same place over and over and over again. They appear to be driven by Earth's tides. That's a bit of a mystery because the strength of the tide is less than 1/100th of a megapascal. That's a tiny number. And why it's strong enough to break a fault deep in the moon is not really clear. The other mystery associated with this is that almost all of them seem to occur on the near side of the moon. And there are two explanations for that, and we can't distinguish between them. One is it may be that the near side of the moon has a little bit of water in it that actually lets the faults be slightly weaker than they would otherwise be, and it lets there be motion on these faults, and maybe the far side of the moon doesn't have that. The other possibility is that there are moonquakes on the far side of the moon, and we simply couldn't detect them with our stations that were in the center of the near side because as the signals went through this molten layer of the moon, or this potentially molten layer of the moon, they were simply absorbed and attenuated. So the way we can actually distinguish between these two very different models of the moon is to put seismometers down on the edges of the moon and on the far side of the moon, and we can actually see what's going on both the near side and the far side and to compare them. And the final type of moonquake is what we call thermal moonquakes. The moon has a day, if you will, when the sun is in the sky that is the equivalent of 2 weeks on the Earth. And so it heats up rapidly after sunrise and it cools down rapidly at sunset. And so these changes in temperatures in the rocks drive small amounts of stress that essentially cause some of the surface rocks to fracture. So this creates some very small, very shallow events. There are ways that boulders essentially break down. They're not dangerous. It's just a way the moon's crust evolves. So I'd like to turn my attention now to understanding the thermal structure of the moon. Recall that we talked about how we used heat flow experiments at Apollo 15 and Apollo 17 to measure the rate at which temperature increases with depth in the moon. That tells us how rapidly heat is coming out from the interior of the moon. Those numbers are 21 at Apollo 15 and about 14 or 15 milliwatts per square meter at Apollo 17. That's between 20 and 25% of the heat that's coming out of the Earth. We would expect that to happen on a small body like the moon because small objects cool off more rapidly, and so naturally the moon has less heat coming out of it now. It turns out, however, and we did not know this when we picked the Apollo 15 and Apollo 17 landing sites, but the moon has a very unusual distribution of radioactive elements. There's a structure known as the PROCELLARUM KREEP terrane. KREEP is an acronym for the chemical term K for potassium, REE for rare earth elements, and P for phosphorus. It's enriched in a lot of elements that include radioactive elements like uranium and thorium. And so it's easy to map from orbit with a gamma ray spectrometer on Lunar Prospector. We know about this now. We started to learn about this at the end of the Apollo mission. Apollo missions, Apollo 15 and 16, but we did not know when we put the Apollo 15 and 17 stations down that these were unusual locations. And the fact that there's a lot of radioactivity in these areas is feeding into the surface heat flow, and so they're not representative probably of all of the moon. We would like to go back with these experiments in other parts of the moon, the places that are purple in this map that have less radioactivity in them, that represents more generally what the moon is like. Another way that we can make estimates of the thermal structure of the moon is from electromagnetic sounding. We can use the response of the magnetometers from Apollo as the moon moves in and out of the Earth's magnetic field. The moon responds to that magnetic field with a magnetic field of its own. We can, in essence, measure what's known as the electrical conductivity of the mantle as a function of depth, and we can relate that to temperature and to composition. So the purple in this graph shows an estimate of what the temperature of the moon is like as a function of depth from seismology and heat flow. It doesn't show the moon melting at great depth, so this is an interpretation. Remember I said that the data might permit melting, but it doesn't require it. This particular study assumed it was not molten at the bottom. But that's an independent estimate of what the temperatures are. And if we know what the temperature is, we can then ask the question, what composition do we need in the mantle to reproduce the magnetic response of the moon? And it turns out if the moon is completely dry, we can't reproduce it. So the dry curves there don't work. The curves that work better are the ones that are in red or maybe in yellow. Those go through the data set for temperature as a function of depth. They assume that there's between 10 and 100 parts per million of water in the interior of the moon. Back during the Apollo era, we thought the moon was completely dry. We thought that was a constraint on how it formed. We thought that based on looking at the rocks. In the last 10 years, since around 2008, studies of the moon from orbit, studies of lunar rocks with new and better instrumentation, is showing that the moon has small amounts of water in it. And this type of experiment is letting us see what's happening in the deep interior, much deeper than any of the rocks we can get at. And this is an example of how the various geophysics experiments work together, how you work with the seismology and the heat flow and the electromagnetic sounding, the data all together to produce one common interpretation of the moon. It's not each experiment telling you one thing, but the experiments together tell us a lot. And then let's also talk briefly about the moon's magnetic anomalies. These have been mapped from orbit. Mostly the moon does not have a magnetic field of its own at present, so that tells us something about what's going on in the core. The moon apparently did have a magnetic field in the past. Almost all of the structures that are seen in this, all of the colored structures on this map are associated with impact basins, and often they're at the antipode of the impact. So the magnetic field gets distorted from the plasma in an impact, and it concentrates the magnetic field locally. That's our understanding of it. So many of the structures that are prominent in the right-hand image are at the antipodes of the Imbrium and Stratitatis impacts. It tells us that the moon had a magnetic field at the time of these impact basins 3.9 to 4 billion years ago. Certain Apollo samples also tell us that the moon had a magnetic field at the time. That's an interesting mystery. Because the moon is so small, it's hard to drive a magnetic dynamo in the moon's core. That's something that happens naturally in the Earth even at present, and we don't really understand it for the moon right now. Some models say it does work, other models say it doesn't. One possibility is that the moon was closer to the Earth early in its history, and the Earth's tides may have helped stir the core and created the conditions to drive a dynamo in the liquid core that way. We don't really know. And again, understanding the structure of the core better, the structure of the inner core, the outer core, the thermal state of the moon, will help us to better constrain this part of lunar history as well. So let's summarize some key unanswered questions. There are a number of things we do know very well, but there are a number of things that we have not yet figured out, that were only hinted at in the Apollo data. The first is that we do know the moon had a magma ocean. There are hints of this in the seismic data from Apollo, but there's still the question remains, is the lunar mantle chemically stratified from magma ocean solidification? This is a signature of how the magma ocean evolved on the moon that is lost on Earth, and that's why we want to go back to it. Is the base of the mantle, the rocky part of the moon, is it still partially molten? Because again, that would be a signature probably of how the moon's magma ocean solidified. How much of the core is still liquid? That again is a constraint on the present thermal properties of the moon. And finally, how seismically active is the far side of the moon? The near side we know is very active. The far side is still a mystery. And there are two different models that we talked about that we can resolve the choice between them if we actually have a new set of seismometers on the moon. So where would I go? The first station I would put down, the star in this map, is either the Apollo 12 or Apollo 14 landing sites. And the reason I picked that to start is that we know what the various moonquakes, the deep moonquakes that from different locations look like at those locations. So we can start by identifying them in this. Plus, this is a location that's at the heart of that PROCELLARUM creep terrain, so we can measure that part of the moon in a way that's even better than at Apollo 15. The second station I would put in on the right, the star in the MARE basin. This is one of the thinnest places of crust on the moon. That means the concentration of radioactivity that naturally occurs in all crustal material is not present. And so this is a good place to go to figure out just the radioactivity in the mantle of the moon, to separate the radioactivity from the mantle and the crust. And that's a good way of understanding the differentiation of the moon. The third one I put on the western limb of the moon. We know that there is one of the deep moonquake nests that occurs on the eastern limb of the moon. Those waves would go through the center of the core, and if we put a seismometer on the western side of the moon, we could actually look for the structure of the seismic waves going entirely through the core. That would tell us a lot about the deepest structure of the moon. And then I would put a station in the thickest part of the crust on the near side, which is the red and yellow part of the topography, because just as we wanted to separate out the signature of the mantle in Mare Crisium, we could learn more about the signature of the crust, both the seismic signature and the heat flow signature if we go into an area of thick crust. And we also have to acknowledge that NASA's plans include the likelihood of wanting to put a moon base at the rim of the South Pole Aitken Basin. So we'd have something at the South Pole. We might also want to put a station near the North Pole of the moon. So with a network of 4 to 6 stations, we could have a globally distributed data set for the near side of the moon. It would get us much better resolution of what's going on in the deep moon than we did with Apollo. So what would I put there? Well, I would put all of the instruments we used on Apollo at all of these stations. I would put down a seismometer. I would put down both a magnetometer, but also I would measure the electric field, because if you measure both the magnetic and electric fields at the same time, you can do a better job with the magnetic sounding of the moon. I would put down a heat flow experiment, which is somewhat challenging. You have to drill a hole down to about 3 or 4 meters depth. That was hard for the astronauts on Apollo 15 and Apollo 17. So this is an engineering challenge, but it's got great value for understanding the thermal state of the moon. And finally, a small laser reflector to expand our reflector network and measure the moon's response to tides. And I would put all of those instruments down at all 6 of these stations if I could. Some of them, the laser reflectors and the heat flow experiments, could be deployed one by one. They don't have to be measured at the same time. The laser reflector is unpowered, so it would work for any length of time. The heat flow experiment could run for one version of the experiment could be over in a week or 2, so it potentially could be deployed even on a commercial spacecraft that might only stay there for 1 lunar day. But if it could be deployed for longer, it would be better. On the other hand, the seismometers have to work as a group. And they're better off deployed for a longer period of time, because the more events you detect, the better off you are. So ideally, this is a network we would deploy in over a period of a year or 2, and then keep them alive for 5 or 8 years together, and that would let us do vastly better than we did with Apollo. We would also like to deploy experiments on the far side of the moon, and I'm going to suggest at least 3 places. The South Pole Aitken Basin is the largest impact basin we know of in the solar system. It's an important place to study the structure of the crust and the impact melt if we want to understand the role of very large impacts in the early solar system. So the center of the basin would be a good place to go. I would also put a sensor in the center of Mare Moscoviense in the northern part of the far side. That is, according to Garel data, the thinnest place, the thinnest crust anywhere on the moon. So again, that's a great place to go to understand the flow of heat out of the moon without the interference of the crustal rocks and the radioactivity in crustal rocks. And finally, I would put a sensor somewhere in the thick part of the crust in the highlands of the moon, because that would let us, again, learn something about the distribution of radioactivity in the crustal rocks. It would let us measure the seismic properties of the crustal rocks. These rocks are left behind from the magma ocean. It would be an interesting question, is there layering within the rocks, for instance? And there's hints of that in Apollo, but we don't really know. So this is the kind of network that we're getting to the point where we might be able to do. NASA's planning commercial payloads. They're actually starting to put contracts out for experiments. So this would be something we'd like to do. Or with the Artemis, anytime people go anywhere on the moon, we should put down seismic experiments or this whole geophysics network. The only thing about the far side experiments is we do need radio communication. The ones on the Earth can talk directly to Earth. If we're going to put stations on the far side, we need radio communication from a satellite in orbit. And we don't need laser reflectors because obviously we're not going to have Earth telescopes seeing them. But otherwise, the far side stations could be identical to the ones on the near side. Maybe a little further in the future, my pipe dream would be that astronauts will do long duration traverses across parts of the lunar crust. NASA is testing out rovers that have the capability of roving for potentially hundreds of kilometers. And I would love to see an experiment where the astronauts got out every, say, 25 or 50 kilometers and deployed a seismometer in a long line and deployed in different places small explosive charges. Now you're thinking, oh, that's dangerous. We shouldn't have astronauts around explosives. But we actually did that in Apollo. On Apollo 16, they used a small mortar, explosive charges to learn about the structure of the moon. On Apollo 17, they deployed explosive charges that were activated by radio after the crew left. And we learned, by the seismic waves from that, we learned about the structure of those particular locations. I'd like to do it on a larger scale. These are the kinds of techniques actually we use on Earth all the time to map out oil deposits, salt domes and things in the Gulf of Mexico. Not necessarily with explosive charges, but that's how we could do it on the moon. And I would love to see us do that over a large impact basin like the Mare Orientale basin, or just a piece of the highland crust that would be the remnants of the magma ocean. These, as I've gone back to over and over again, these are places that they record the early history of the moon and the early history of the Earth, but there's not left on the Earth anymore. So to wrap up, we know a lot about the structure of the moon, the interior of the moon, from the combination of Apollo data and the various satellites like GRAIL and Lunar Reconnaissance Orbiter. We know that the moon is differentiated into a crust, a mantle, and a core, a rocky outer layer, a rocky middle layer, and a metal-rich inner core. The crust and mantle preserve signatures from the early magma ocean phase of the moon. They also preserve signatures from the moon's impact history, and these are intrinsically worth studying because the Earth went through the same process, but it's not preserved there. The physical state of the lowermost part of the mantle and core provide important constraints on the moon's overall thermal evolution. So we would understand how the moon was behaving if our models have to be able to reproduce the current state of the moon for us to have confidence that they're telling us about the early history of the moon as well. So if we want to understand, for example, when the moon created magnetism, we'd like to be able to understand the present state as well. And I'll emphasize that a new generation of globally distributed geophysics stations that could be deployed robotically, could be deployed by human crew, but across the entire part of the near side, hopefully also on the far side, this globally distributed network will provide important new insights to the early evolution of all of the terrestrial planets, not just of the moon.